Hi, I'm Dr. Tim Komar, and today in this video, we will give a couple examples of implicit differentiation. Implicit differentiation is used for differentiating when we're not able to solve explicitly for y as a function of x. So, quick review of what the procedure is. We're going to consider an equation in terms of x and y, where typically we're not going to be able to solve for y in terms of x. And to calculate the derivative dy dx by implicit differentiation, we're first going to think of y as an implicitly defined function of x. We will then differentiate both sides of the equation with respect to x. And the key thing here, when differentiating terms involving y, remember that y is a function of x and use the chain rule as needed. And then we solve the resulting equation for dy dx. And we're done. Here are two examples. So the first case, we are going to use implicit differentiation to calculate the derivative of y dy dx from this equation here, y squared minus x squared y equals sine of y. So first thing we do is we differentiate both sides of the equation here. And I'm using this operator notation over here to remind us that we are differentiating with respect to x over here, and later on writing the derivative in the Leibniz notation over here so that we can remember that y is a function of x and the derivative is a function of x. Okay, so back to the differentiation here. Very simply on this first line here, I just split apart this difference into the difference of these two derivatives, and then we start calculating the derivatives here. When I calculate the derivative of y squared, we are going to need to use the chain rule. So the outside function here is squaring, the inside function is y. The derivative is going to be 2y times dy dx here. Next, when we take the derivative of x squared minus y, we need a product rule here. So here we're going to need the derivative of x squared, that's 2x times y, plus x squared times the derivative of y. And lastly, over here, we're going to need another chain rule here because we're taking the derivative of sine of y. Sine is the outside function, y is the inside function, so we're going to get cosine of y times dy dx. Now we've done the differentiation. Now we need to simply solve for the derivative dy dx. So what we are going to do, we just expanded over here, distributed that negative sign. And now at this point, we want to get all the terms involving the derivative dy dx onto the left, all the other terms onto the right, and we've done that right over here. So the only thing we needed to move over to the right-hand side was this 2xy, and the only term we needed to move over to the left-hand side was a cosine y dy dx. And we just factor out that derivative here, and in the final step, we divide, and there is our derivative. But notice here that this derivative is expressed in terms of both x and y, which is typically what happens with implicit differentiation. Here's another example where we want to find the derivative dy dx here. This time the equation is y cubed plus y squared times e to the 3x equals natural log of x squared plus y squared over here. Part of the reason that I picked this example is I wanted to make sure that the algebra steps are going to be done carefully as well. And I've pointed one thing out on the following slide over here. So again, we start by differentiating both sides. And here, when we compute the derivative of y cubed, again, we're going to need the chain rule. That's going to be 3y squared times the derivative of y. The y squared times e to the 3x is going to require another product rule. So here the derivative of y squared is 2y dy. It's using chain rule again. times e to the 3x plus, and then we're going to have y squared times the derivative of e to the 3x, which is this 3 times e to the 3x over here. On the other side, the derivative of the natural log function is 1 over its inside here, so it's 1 over x squared plus y squared times the derivative of that inside here, which is 2x plus 2y times the derivative of y here. Notice when I expanded this right-hand side using the distributive rule here, I wrote this in red over here. It's important to know that, again, this factor of 1 over x squared plus y squared is multiplied by the 2x and the 2y times dy dx. I have seen many students run into trouble with the algebra at this particular point over here. So I wanted to point that out for you. So now what we are going to do is solve for dy dx again. We're going to move all the terms involving dy dx over to the left-hand side and factor out the dy dx like we did in the previous example. Move what turns out to be only two other terms over to the right-hand side, and we divide. And I'm going to leave it in this particular form over here as trying to write everything out, threw off the typesetting over here, and this is a little bit easier to manage at this point. So again, I'm Tim Komar. I'm available for mathematics tutoring for all high school and college mathematics courses. Please like this video, subscribe, watch other videos, and contact me for tutoring. Take care.